Here are a few more types of variation. If we have y equals k times x to the n, we would describe this as y varies as the nth power of x, or y is directly proportional to the nth power of x. The second one here, y equals k over x to the n. This is an inverse relationship now, so we'd say y varies inversely as the nth power of x, whatever that power n is, or y is inversely proportional to the nth power of x. We'll take a few examples of these types of relationships. When brakes are applied, the distance for a car to stop is directly proportional to the square of its speed. So as you jam on those brakes, push on those brakes, the distance required to stop is directly proportional to the square of the speed that you're going at. If a 40 mile per hour speed needs 200 feet to stop, how long does a 60 mile per hour speed require to stop? And this is for a particular car. For different cars and vehicles this would be different. But for this example, we have a direct relationship directly proportional to the square of its speed. So let's call distance d is equal to k, distance d, and we'll call speed s. So d is directly proportional to the speed s squared. In addition, we're told that d is 200 feet when s is 40. So 200 is equal to k times 40 squared. We need to solve this equation for k. We divide both sides by 40 squared. So we have 200 divided by 40 squared equals k. And so k is equal to, we do this calculation, .125. So now we can plug this 0.125 back into our equation here to have the equation for the relationship between distance and speed. So we're told the distance is equal to 0.125 s squared. We've just calculated that. And we know now the question is saying, well, what if s is 60? If s is 60, what's our distance going to be? Well, d will equal to 0.125 times 60 squared. And so d will equal to, when we calculate this out, we get 450 feet. So notice that the distance actually has doubled, even though we've gone up by 20 miles per hour. The distance has more than doubled that it takes to stop. And that's because of that square relationship. The weight of an object varies inversely as the square of its distance from the center of the Earth. If a person weighs 180 pounds on the Earth's surface, what is his weight 100 miles above the surface? Assume the Earth's radius as being 4,000 miles. Now we're given an inverse relationship here. What are we given? We're told that the weight, we'll say W, varies inversely proportional to the square of the distance from the center. So we'll call that d for distance from center squared. It's an inverse relationship, so it sits in the bottom. And we have a k up here. So W equals k over d squared. That is our relationship. Now we're given a weight and we're given a distance. On the surface, which is 4,000 miles away from the middle of the Earth, the weight is 180. So we're told 180 equals k divided by 4,000 squared. So we want to solve this for k. We multiply both sides by 4,000 squared. So k is going to be equal to 180 times 4,000 squared. We need to plug that in our calculator, and we get k equal to 2,880,000,000. That's our k. So we could plug this in for k here and continue on with the problem. So we're asked now, what if you go 100 miles further? What is the weight of this person going to be? So we know W is 200 2,880,000,000 divided by d squared. We need to plug in our new distance. Our new distance is 4,000 miles plus 100 miles because going up a further 100 miles from the surface. So our new distance will be 4,100 miles. And we have to square it. And so now we perform our calculation. 2,880,000,000 divided by 4,100 squared, we get W equal to 171.3 pounds. And so there's an application of inverse square variation.